Okay, good evening to all and welcome to the another session of the NPTEL course Heat Transfer. This is our ninth session. Today we will be discussing the topics related to the contents that were topics covered in the week 9 of the course. Which is basically the condensation and the chart of radiation. So, in the last week we discussed about boiling. So, here the condensation is just a reverse of boiling, where the vapor or the vapor will get condensed when it actually meets a surface which is below the saturation temperature of the vapor at that particular pressure. Okay, so that is basically the condensation, and different types of condensations are there. Basically there are two types, that is film based condensation and drop based condensation, and it was already discussed in the lectures. And then we move on to the radiation part, which is the third mode of heat transfer. So basically, in this course was divided into like three parts. Like first, we discussed about the convection part. Then we moved on to the convection, and the third mode of heat transfer, which is a radiation, which is basically a heat transfer using the like electromagnetic waves. Okay. So for radiation, what you should understand is there is for conduction and convection there was a need of medium, but in radiation there is no need of any medium. So any substance or any object which is above the 0 Kelvin emits some radiation, but the amount of the the value, whether it is significant or not, it depends upon the temperature uh, of the body. So basically, I hope you are aware of some IR, infrared thermal cameras, which is very common during the COVID times. So usually when we so during, I hope you are aware of that. That like, and you will be check the temperature. It's like a non-contact measurement. So it is like our body has a certain temperature. So it emits radiation based on the temperature of the body. A thermal radiation will be emitted based on the temperature of the body. So that device is calibrated with different temperatures. So what is the wavelength it is receiving and the corresponding temperature it will show. So normal body temperature is say 37 degrees Celsius. So it has a corresponding frequency or electromagnetic radiation. But when the body temperature rises to some say around 40 or 45 or above, the amount of energy radiated will be different. So that is detected by that object, and the corresponding through proper calibration, the corresponding temperature is displayed. So the radiation has very significance in the practical applications, like we already saw that we experienced during the COVID times. And also, say for example, the temperature or a body having the temperature above 100, sorry, 1000 or above 1500, it's not very easy to have a contact measurement. So in that case, we usually uses like, let's say for example, a moving object which is having say around more than this 1000 or something. And so we usually go for this non-contact type of measurement, that is using an IR camera or thermal sensors. So that is the significance of radiation. Okay, so let's move on to the first question. First, we will start with some condensation questions, and then we will move on to the radiation part. So here we have a condenser of a steam power plant which operates at say uh, at a pressure of 7.38 kilopascal. And the steam at this pressure condenses on the outer surface of a horizontal pipe through which the cooling water circulates. The outer diameter of the pipe is 3 centimeter, and the outer surface of the pipes are maintained at 30 degrees Celsius. To determine the rate at which the heat transfer to the cooling waters, rate of heat transfer to the cooling circulating water. So I will give some time to solve. So can you please say what is the saturation temperature, or at what temperature the steam is condensed? Because it's already given in the question. Any idea? It's given by the outer surface of the pipe is maintained 30 degrees Celsius, which means the steam is condensing at 30 degrees Celsius. So that information can be avoided. Means, say for example, in some questions you will be this kind of question we already discussed in the previous session. So instead of directly giving this 30-degree value, so it will be simply said that the steam at a pressure of 7.38 kilopascal condenses on the outside surface of the pipe. So that is enough to find out what is the temperature of the pipe, or that has the temperature at which the steam is condensing. How, if the pressure is given and it is given, how to find out at what temperature it is condensing?
That is from the steam table.
Yeah, you can directly find out from the steam table, but here it's not necessary, it's already given. So I'm just mentioning, if it is not given, you can find out easily from the steam table. Okay, so I hope you are able to solve it. Okay, we will solve together. Can you please say how to solve this thing? Yes. Okay, we have a cooling pipe. Okay, so we have a pipe through which cooling water is flowing, and the outside surface, the temperature or the steam is condensing at a temperature of 30 degrees Celsius, which maintains the outer surface of the tube at 30 degrees Celsius. So we are asked to find out what is the Q, that is the heat that is gained by the cooling water. Okay, so we have some assumptions like it is steady state and the tube wall is entirely isothermal with 30 degrees. So some assumptions we are taking, like first is steady state assumption, and second is the tube is isothermal, which means there is no, the entire tube wall is maintained at 30 degrees Celsius. Okay. Then I will give the properties at of the steam at 3.8 kilopascal, which is HFG is, this all you can find out from the steam table, but I'm just directly writing. And rho V is 0.05 kilogram per cube. Then, the properties of liquid water at film temperature. Usually the when we deal with boiling and condensation problems, we will use the properties at the film temperature. Okay, which means the T saturation or the T surface plus by 2, which is around 35 degrees Celsius. Okay. So then we have the properties I am writing. Then Cp value. Mostly in the question, this all will be given. Otherwise, you can find out from the data book. Okay, these are the given values. So actually, we have to find the modified. So before that, I have to find out the heat transfer. Let's find out what is the heat transfer rate, that is the condensation heat transfer rate. So if we are assuming there is no heat losses, whatever is the condensation heat transfer is the heat gained by the water. Okay. So So this correlate this expression is already discussed in the class, so I am directly writing the H for it horizontal to it is around 0.729 G rho L. Sorry, rho L minus rho V HF G star. This is the modified specific heat. Okay, sorry, latent heat. KL Q, that is K, that is the liquid divided by mu into T sat minus T surface. Okay, so raised to 1 by 4. So can you please find out? Okay, actually, I think I made one mistake. So the tube surface for say for example, for the condensation to happen, there should be some degree of superheat or subcooling. So, okay, actually the TS, so the T saturation we have to find out. So this is the T surface. That is the surface is maintained at 30 degrees Celsius, and we have to find out the T saturation at this this uh, pressure. So can you please find out and say from the steam table what is this? What is the saturation temperature at 7.38 kilopascal? So I made a mistake there.
Steam table I'm not having.
You can just Google it. You will get the properties of steam at different pressure. You can just search. Have you find it out? I think it is close to around 40 degrees Celsius. Okay. You can verify later. So can you please so now we have to find out what is the modified modified latent heat which is given by HFG star is equal to HFG plus 0.68 times CPL Tsat minus Ts, which is equal to 2470 into 10 raised to 3 plus 0.68 into 4178 into 40 minus 30. Okay. 2435 kilojoules per kilogram. That is the modified specific heat. Now we can just directly apply. So as you know, this rho L minus rho V, this rho L is very much greater than rho V. So I'm writing rho L minus rho V is approximately equal to rho L. Okay. So H I am replacing it as the expression as G rho L square HF G star KL cube divided by mu L into T sat minus Ts times D. So if you can substitute the values, rho L is 9 HFG star KL 0.623 mu L T sat minus Ts is 40 minus 30 into D is diameter 3 centimeter. So 0.03 always. So this will come out to be around 2. So this is the heat transfer coefficient in this case. So now what we have to find out, Q is equal to H, the surface area, times T sat minus Ts. Okay. So this is equal to H times pi T. So here we are asked to find out per length. Okay. Of heat transfer circulating in the water per length. Okay. So per unit length. So I'm taking L as 1. So or pi D into 1 times T sat minus Ts, which is equal to 9292 into pi into 0.03 into 40 minus 30, which you will get at 58 watts. So this is the condensation heat transfer. So this will be the heat that is gained by the cooling water. Are you agree or not? Because we are assuming that there is no heat losses, whatever the heat gained by the whatever the condensation heat transfer is going to the circulating water. So I hope this question is clear. So these expressions are always discussed in the lectures. If you have any doubt in the how it came, you can just refer back to the lecture. So uh, it is derived in the lecture how this h value, this expression must be. I hope you watched that lecture.
Yes, sir.
Okay. Then we'll move on to the next question. We have to find out the rate of condensation per unit length of the steam horizontal pipe. So so this is just a single step solution. So
This question I'm not able to recall why we are using this modified latent heat.
actually it is because of some convection effects will also comes into play, because it is like uh, it is this modification is basically uh, uh, what to say, suggested by Rosnos. Okay, so if some in the modify there as you know there will be some convection effects also in this during this condensation reaction. So there is some it is included. It this was made by, if I remember, it was made by Rosinos and Nasser, I think. Okay. They point out that there will be some thermal advection effect is also there, which should be added to the latent heat of vaporization. So the Rosinos only recommended this modified latent heat form, which adds an additional term of 0.68 Cp Tsat minus Ts. Okay. So if you take HFG common, you will get you will get a new term which is known as a Jacob number, which is the ratio of that is the sensible heat transfer to the latent heat transfer, which is like Cpl Tsat minus Ts by HFG. That is the Jacob number. That's a new number that was introduced. I hope it's clear.
Yes, sir.
So I will give some 2 3 minutes for you to solve this. Okay. This is just a simple expression. I hope you will get. Did you got the answer?
Actually, that latent heat data I'm not having because I have to divide this rate of heat transfer from with the latent
Oh,
heat.
yeah.
The
Okay.
latent
Yeah.
heat
Condensation is equal to Q by HFG. Okay. So Q is 85. So
eight
85
eight seven eight seven eight
divided by
seven five eight.
HFG. What we find out is 2435 10 raised to 3. So it will come out to be around 0.00360 kilogram per second per unit length of the tube. Okay. Now we'll move on to the next question. So can you please move? I am getting some echo. Yeah. So we have to in the previous case only. So previous problem, instead of a single pipe, okay, we have 12 horizontal tubes arranged in the rectangular array of 3 tubes high and 4 tubes wide, as shown in the figure. So the same tube that we discussed in the previous question. So now it's not a single tube; it's an array of two. Okay. So in this case, we have to find out what is the total rate of heat transfer and the rate of condensation per unit length. Can you say how we to proceed, how to find out? This is the case of condensation on an array of tubes. Okay.
We have to use that in the expression the number of tubes which are vertical, that is three.
Hmm.
Because in this the condensate of one tube is falling on second and the second tube condensate is falling on third.
Yeah.
So there will be definitely effect on the heat transfer coefficient H.
on this horizontal tubes, right? In this array of tubes, which means the condensation heat transfer is not influenced by the presence of tube in its neighboring. Okay, so which means this is not influenced by the condensation of this tube. This tube is not influenced by this tube. Okay, but this is influenced by the tubes that is in this direction, this vertical direction. Okay, which means the condensation that is formed is falling onto the tube just below, and it is falling to the tube just below. So the condensate is influenced by in this direction. This is not on this array. Okay, I hope you understood. This four vertical tubes, it is influenced, but not in the adjacent neighboring tubes. Okay, so we have the equation of horizontal for n tubes, which is in the vertical array. It is 1 by n raised to 4 h horizontal of a single tube. So can you please say what is the n value of n here?
So N is 3.
Yeah, n is 3. So it is equal to 1 by 3 raised to 1 by 4 times what is the horizontal we already. So you will get a expression of what is the horizontal tube, right? So I think now you can solve. I will give some 2-3 minutes for you to solve. You have to find out the same in the previous case, the total heat transfer rate and also the condensate per unit length, total condensation rate per unit length. So we can find out the same way we have find it out earlier. So you can find out H, then from then total condensation area, then divide it by the HFG, you will get the condensation. So I will wait for 2-3 minutes. Do you need any data to solve this? You can ask. I will write it here. I think you may need D, which is 3 centimeter. So it's asked to find out per unit length. So that is also not required. So T saturation is 40. The surface temperature is 30 degrees Celsius. And the HFG you may need, which is 2435 into kilojoule per kilogram. I think this is the only data you require to solve this. So I'll wait for 2-3 minutes. Did you got the answer? What is this H value of N2?
Sir, H is 6650.9. No, no, 7060.39.
7060.
Point 39.
Then what is the Q? How you find out?
That I have used this HN, that H horizontal N cube multiplied by area multiplied by
N
something
times
and
by D. Yes, it is unit length, so I'm taking L as 1. It is at n space, which is equal to 7060 into what is the total number of tubes? 12 into what is D? 0.03 40 minus 30. So what is this answer?
uh, actually I didn't multiply it by number of tubes.
Yeah,
So
because we are asked to find out the total number, right? Total heat transfer. So we can verify later. It will come out to be around.
79810.
Okay.
Yeah, 79810.
Yeah. So now condensate is just divide.
It by the latent heat.
So it will come out to be around. So this is the answer. You can cross verify later. I hope you got it.
Yes, sir.
So now we'll move on to the next question. So this is a question from radiation part. So these are the condensation questions. So you can expect a question like the previous one I have discussed. But so if you refer to some of the textbooks like in Proper and all, so the condensation there are different regimes are there like wavy regime, laminar. Whatever we have done is under the assumption that it is the condensate film is laminar. Okay, so then there is another regime like laminar, wavy, turbulent. So so these expressions, whatever I have used, is not applicable under that region. So it has separate expression for this region. So you can refer to the textbook and you can find it out. Okay. So now we will move into the radiation part. So here we are giving a spectral distribution of radiation emitted by a diffuse surface, which is approximated in this figure. We have to find out what is the total emissive power and the total intensity of radiation emitted at an angle of 30 from the norm. So can you find it out? Can you say how to solve this problem? Here the emissive power is a function of lambda. Okay.
But this emissive power can be found by calculating the area under the graph.
Yeah.
So it will be simply 5 multiplied by 100, then 5 multiplied by 200, then again 5 multiplied by 100. So we will get the total emissive power. That will come out to be 2000.
Yeah. So as it is a simple structure, it's like area under. It's basically the area under the curve. But if it is not, if it is some function, you have to integrate. So the basic is so. One more thing, you are asked to find out an angle of 30 degree from the normal. So can you please mute? Yeah. So that is that is not relevant here. Why? Because this is a diffuse surface. It's already given the diffuse surface. So the diffuse surface, the emission is independent of the direction. Okay. So we can simply calculate the uh, E value. So E total is equal to integral. So this is I'm considering this as a different regions like 1, 2, 3, 4, 5. Okay. So first E lambda d lambda plus integral to E lambda d lambda plus integral 3 E lambda d lambda plus. So this is basically like 0 to 5 0 d lambda plus integral 5 to 10 100 d lambda plus integral 10 to 15 200 d lambda plus integral 15 to 20 100 d lambda plus equals 50 sorry 20 to say infinity 0. So these are 0. So it's like simply 100 into 10 minus 5 plus 200 into 15 minus 10 plus 100 into 20 minus 50. So as always we'll get to 100 watt per meter square. Okay. So that is the first question. So can you please find out what is the intensity, total intensity of radiation? What is the relationship between intensity and total emissive power?
Is equal to pi I.
Yeah, you can just simply find out the I as E by pi. So what is the answer? Can you calculate and see?
It's 637.
How much?
637.
6, 3. So we'll move on to the next question. So we have considered a large isothermal enclosure that is maintained at a uniform temperature of 200 Kelvin. Okay, sorry, 2000 Kelvin. And what is the wavelength below which 10% of the emission is concentrated? And determine the maximum wavelength at which the emission occurs.
Sir, actually, that previous question, it was the diffused that transmission,
Yeah,
diffused emission. So
yeah,
will the intensity will be also be uniform?
yeah,
In
yeah.
all,
Both the diffuse surface, it is independent of direction. The density is independent of direction.
so intensity will also be independent of the
Yeah,
direction
yes,
as well as the emissive power.
yeah.
Okay.
So you can try this question. So you may need this data or this chart. So if you can write down the necessary points, and after that I will go on to the next page. Okay. calories, I will write the things here. So the T, that the body temperature is 2000 Kelvin. Okay. And you are asked to find out the total emission, the 10% of the total emission. What is the wavelength below which the 10% of the emission occurs, and also the wavelength at which the maximum emission happens. That are the two questions you need to find. So you can use this table to find it out. So if you are you, will you try or I should start solving?
So actually, this maximum wavelength, I hope that it will be collected from the Wien's displacement law.
Yeah, yes.
But the 10% of emission, I don't know.
Yeah. Then you calculate the lambda max. I will explain how to calculate.
Lambda maximum is around 1.5
1.5 unit.
micrometer.
Yeah. Okay. So first we will. So that comes from the Wien's displacement law. That is lambda lambda T max is equal to 2898 Kelvin. Okay. So lambda max is equal to 2898 divided by T, which is equal to 2898 divided by 2000. Yes. So this is the wavelength at which the maximum emission happens. Okay. So if you check the distribution, so the distribution function will be somewhat like this. Okay, at temperature 1000 Kelvin. So what we found out is this lambda. This lambda is 1.45 micrometer. But in the question, we are asked to find out the wavelength below which 10% of the emission is concentrated. So this starts, say for example, this is the 10% emission region. Okay. And we are asked to find out this lambda one. Okay. So 10% region. So this is given by a function known as black body radiation function. Okay. So this function, if we write in the functional form, so the f0 to lambda is equal to integral 0 to lambda, that is from here to here, eb lambda d lambda divided by integral 0 to infinity e lambda. So this function is represented in this box, in this table. So this will be very helpful, or this will be very helpful to find out this type of problems. Okay. So 10%. So what is the 10% of the total emission? So we have to check where the f lambda becomes what value from this. 10% of the emission means what should be the value of f? I hope you understood what is f. So f is the percentage, like 10% means So from here to here, some part divided by the total emission. That is what F. So in the question it is asked 10% of the total emission. Then what should be F here from this table?
Sorry, it should be 0.1.
Yeah, it should be point. So from this, the point one is we have to consider this one. Okay. So what is the lambda t corresponding to this? For F0 to lambda 0.1. So the lambda t close lambda t is 2200. Can you please mute? Then so the temperature is known. So lambda is equal to 2200 divided by 2000. So which is equal to 1.1 micrometer. Okay. So this lambda 1 is 1.1 micrometer. So below this wavelength range, the 10% of the total emission happens. So I'm giving another example. So can you please find out where at what lambda, say for example, 70% of the wavelength happens. You can take a nearest value of f function. So want to know below what wavelength this 70% of the uh, total emission happens. So you can use this table and find out. I'll give you some 2 minutes. Yes, I want to make you familiar with the table because the rest of the all the problems you have to use this table. So unless you are not comfortable with taking values from the table, you will not be able to solve the problem. At least say the what is the lambda t, the product at 70% of the total emission.
5,600.
Yeah. So lambda t is 70% of the emission is occurred. Lambda t is so f0 to lambda, which is 0.7 I am taking. So the closest value 70 is this one. Okay, 5,600. So lambda is equal to. So what is this answer?
2.8.
So this is how you can use the table. So you can take a screenshot of this table because the rest of the question you may need this. I hope you have taken. This table is available if you search any heat transfer textbook. I have taken it from in Coursera. Fundamentals of heat and mass transfer. So we'll move on to the next question. So we have if the sun's equivalent black body temperature is 5,800 Kelvin, determine the wavelength corresponding to the maximum emission. That is first part, and also determine the fraction of the emission that is emitted in the following spectral regions. Okay, first is ultraviolet, second is visible, and third is IR. First you calculate what is the uh, wavelength corresponding to the maximum emission. Then we will move on to the proceed to the next part. What is the wavelength maximum corresponding to the maximum emission?
0.5 micrometer.
Yeah. So the temperature of the sun is 5800 Kelvin, and lambda max T is equal to 2 micrometer, which comes from the wind's displacement law. So the lambda max is equal to 2 temperature 5800, which is approximately. So do you know what is the wavelength range of thermal radiation?
Wavelength range of thermal radiation.
Yeah.
That is electromagnetic.
No, no, I'm saying about the thermal radiation is a part of the electromagnetic radiation. So I'm asking what is the wavelength? It is one part of an electromagnetic spectrum. Okay. So what is the part where the thermal radiation lies? Typical wavelength range. In electromagnetic spectrum, there are a lot of waves like gamma waves, X-rays, microwaves, visible radiation, infrared region. So a region where the thermal radiation lies.
But
It is basically
thermal
the
radiation
thermal.
will be in infrared, invisible in UV also.
Yeah, yeah. So it's typically between zero point 0.1 to 100 micrometer. This region is known as the thermal radiation region. Okay. So in our next question, we are asked to find out determine the fraction of emission which is which is ultraviolet, visible, and IR. So in between this thermal radiation, it's the combination of these. Some part is ultraviolet, some part is infrared, and some part is visible. Do you know what is the visible region? Range? Wavelength range for visible region. UV, visible, and IR. It's between zero point 0.4 to 0.7 micrometer. Okay. This so if this is the wavelength region, if the emission, then only we can see. Okay. So this is the wavelength range between in a visible region. So the infrared is from zero point 0.7 to 100 micrometer, and the UV radiation from 0.1 to 0.7, sorry, 0.4 micrometer. This I am writing in the thermal region, ultraviolet. So ultraviolet go back to 0.01 also. So but the ultraviolet region in the thermal radiation region. Okay, thermal region. That is what I am writing. So from 0.1 to zero point 0.4 micrometer, it's ultraviolet region. And from zero point 0.4 to zero point 0.7, it's a visible region. And from zero point 0.7 to 100, it's a infrared region. So now you can easily solve this question. So you got the wavelength ranges. Okay. Now you can find out what is the fraction where the solar emission is UV, visible, and IR. So do you need this table or you already have? I'm asking about this table.
The table I'm having.
Okay. Then you can find out what is the fraction or what is the fraction of emission in the UV region. So I will give some time. After that, when you complete, you can uh, pick out the answer. Yeah, I will also start solving. So first is the UV region, which is between 0.1 to zero point 0.4 micrometer. So first is lambda 1 t, which is zero point 0.1 into 5800, which is 580 micrometer Kelvin. So we will go back to this this table and check what is lambda t value. So 580 lies between 400 and 600. So this value is f0 to lambda is 0. Okay. So the function is 0. So lambda to t is zero point 0.4 into 5800, which is 2320 micrometer. Will be. Okay. You can go back to 2320. So it is between this one and this one. Okay. So either you can just have a small interpolation, and you can have you can find the f0 to lambda 2 as around 0.1245. So the actual value of FUV is equal to integral zero point 0.1 to zero point 0.4 EB lambda d lambda divided by L0 to infinity EB lambda d lambda. So which is in terms of function, you can get 0 to lambda 2 minus f0 to lambda 1 is equal to 0.1245 minus 0 is equal to 0.1245, which is around 12.45 percentage of the total sun's radiation is ultraviolet. Okay. So can you please find out the second one, visible regions? I already shown how to solve. So visible from zero point 0.4 to zero point 0.7 micrometer region. So first find out what is the lambda t product corresponding to zero point 0.4, then 0.7, then find out the corresponding function, if black body radiation function value, subtracting, you will get the fraction of visible region.
So I got it 28%,
28.
around 28.
Okay, one thing we will solve. So lambda 1t is how much? 0.4 into 5800. What is the answer?
2320.
2320 micrometer. Okay. So we will go back to this one. So 2320 lies between this one. Okay. So we already find it out what is from the previous value. That is 0.1245. Then lambda 2t is how much? 0.7 into 5800. What is this answer?
4060.
460 micrometer. What is f0 to lambda 2? 4060.
0.48.
4060 means between this one it will come, right? So we can write around 0.49. There can be some interpolation mistake, but not that much big. It should be close to 0.491. So just subtract it, f visible, which is equal to 0.491 minus 0.1245. So what is this answer? It should be some close to 0.367. So 36 percentage of the sun's radiation is in the visible region. That's why we are able to see the see what in the daylight. Okay. Now the infrared region. Infrared, which is between zero point 0.7 to 100 micrometer. So lambda 1 T is 0.7 into 5800 is equal to around 4060, so which is 0.4914. Okay, lambda to t is 41, sorry, 100, right? Yeah, 100 into 5800 is equal to 58000 micrometer. So this will be, anyway, I think it's 1. It's going to be 1. Okay, yeah, F0 to lambda 2 is 1. So the thermal radiation part, infrared radiation is F0 to lambda 2 minus F0 to lambda 1, which is 1 minus 0.4914 is equal to around 0.5086. So you can see that the major portion of sun's radiation is in which region?
Visible?
No, check the IR. It's some 50%.
Yeah, yeah. In infrared region.
Yeah, infrared region. So from 50% is infrared, some 36% is visible, and some small portion, 12% is the ultraviolet radiation. Okay, so the sun's radiation is a mix of these three. I hope now you are comfortable in solving the means using the tables. Okay, let's move on to the next question. This is a spectral emissivity, that is epsilon, distribution of a diffuse surface at a temperature of 100 Kelvin, sorry, 1000 Kelvin. Calculate the hemispherical total emissivity of the surface and the hemispherical total emissive power of the surface. These are the two things you need to find out. I hope you know what the expression, that is epsilon, that is the emissive power or emissivity, we will say, is equal to interval 0 to infinity E lambda d lambda, spectral emissivity E lambda divided by interval 0 to infinity the black body radiation, interval 0 to infinity of EB lambda d lambda. Okay, so this we can write as 0 to infinity E lambda uh, EB lambda d lambda divided by 0 to infinity EB lambda d lambda. Okay, so as it is a diffuse surface, we can take this in common E lambda. This is the what is this? 0 to, so, so this is the expression for emissivity. Okay, now we can write it's equal to interval 0 to lambda 1 EB lambda d lambda divided by interval 0 to infinity EB lambda d lambda plus, there are three regions, right? 1, 2, and 3. Integral lambda 1 to lambda 2, the 2 EB lambda d lambda divided by integral 0 to infinity EB lambda d lambda plus integral lambda 2 to infinity epsilon lambda 3 EB lambda d lambda divided by integral 0 to lambda EB lambda d lambda. Okay, so this, in this interval, that is from 0 to lambda 1. So lambda 1 is what is here?
Four.
It is 4 micrometer. Lambda 2 is 6 micrometer, and it's some, that is from infinity. So between this, so from 0 to lambda 1, so E lambda 1 is constant, right? So we can take this E lambda 1 outside integration. Similarly, between lambda 1 and lambda 2, this E lambda 2 that is we are written is constant. So that is comes out, that also comes out of integration. And in the third region also, that is from lambda 2 to infinity, the emissivity is constant. So these the emissivity values of these three regions we can take outside. That is integral 0 to lambda 1 and taking this outside. EB lambda d lambda divided by integral 0 to lambda infinity plus. So what can you identify what is this function? These functions. What are these functions?
No, sir.
Oh, we discussed, right? So it's the black body radiation function. Okay. I
Yes, yes.
already, yeah,
Yeah,
that is a black body radiation function.
yes.
Yeah. So this, so E lambda 1, F 0 to lambda 1 plus lambda 2, F, F lambda 2 to lambda 1 means F 0 to lambda 2 minus F 0 to lambda 1. You can write like this. F uh, F 0 to lambda infinity minus F 0 to lambda 2. Now it's complete. So because E lambda 1 is given, lambda 2 is given, lambda 3 is given. So the only thing you need to find out is what are the black body radiation functions corresponding to this. Okay. So can you please find out what is this these values? This, this, this. So E lambda 1 is already given. E lambda 1, E lambda 2, E lambda 3. These values are already given. That is zero point 0.8, zero point 0.6, zero point 0.7. So I need this black body radiation function values.
Sir, what is the value of lambda 1, lambda 2, lambda 3?
So what is the value of this f0 to lambda 1? So this lambda 1 t is how much? It is point, what is lambda 1? 4 into 2898. What is this answer?
No, sir, we will multiply it by temperature.
Yeah, sorry. Sorry. So what is the t?
1000.
100,000. Yeah.
So
This is
4000.
4,000.
For that, I got 0.48.
Yeah. So the f0 to lambda 1 is 0.48. Okay.
Yes.
So lambda 2 t is some 6,000, right?
Yeah.
What is f0 to lambda 2?
0.74.
Okay. Now it's easy to find out, right? So 0 to infinity is what is f0 to infinity without even like seeing the table we can find out what is 0 to
1. 1.
yeah, yeah. Now what is this? You can directly find putting directly 0.8 into 48 plus 0.6 into 0.74 minus 0.48 plus 0.7 into 1 minus 0.74. Can you calculate what is this? Okay.
0.72.
Yeah, it's close to 0.272 the NSV power. Oh, sorry, NSV. Can you calculate the total NSV power? Hemispherical total NSV power. How to calculate this? EB. Sorry. Stefan Boltzmann law. What is that? Stefan's law.
Sigma A T raised to power 4.
Yeah, that is for a black body. So here we have to
Emissivity. We have to multiply by
multiply
emissivity.
the emissivity. Can you please calculate what is this answer? That is 0.72 into what is Stefan Boltzmann constant 5.67 into 10 raised to minus 8 into it's a temperature 1000. So here the T should be 1000, sorry, it should be in Kelvin or degree Celsius.
It should be Kelvin.
Yeah, that should be, it should be very, it should, when substituting, it should be very careful because in questions they may give in degree Celsius, but in radiation part you have to use Kelvin for every substitution. Okay, for temperature substitution. So can you please find out what is this E value?
40824.
40824
824.
watt per meter square.
Yes.
Yeah. Then it's a part of the next question. Calculate the fraction of total emissive power in this region. So it's same as that of what we did in the our previous part. Okay. So I hope you will be able to solve. I will wait for 2 minutes. The fraction of total emissive power in this region. So in this question, we are asked to find out the fraction of total emissive power in the uh, between this wavelength region. So the required fraction is equal 0 to b into 0 to 6, 6 micrometer. E lambda d lambda divided by equal 0 to infinity E lambda EB lambda d lambda, which is equal to integral 0 to 6 E lambda EB lambda d lambda divided by integral 0 to infinity epsilon EB lambda d lambda. I hope you agree with this. Okay. So from 0 to 6, we have to divide into two parts, right? Because from 0 to 4, it's one emissivity, and from
But
4 to
the
6, it is, yes.
expression you have written, I think this emissivity will not come in the denominator
Why?
because emissivity will be in the denominator and then the total, that fraction we are calculating. So this emissivity should be in the numerator, not in the
Both,
denominator.
both numerator and denominator, it should be there. Because this is not a black body.
Okay.
This is not a black body. That function is for black body radiation. Okay, it shouldn't be confused. It's for black body radiation functions. These functions are applicable for black bodies. So you have to modify our expression so that we can use this black body radiation function. That's what I'm doing. Okay.
But
So
first term you have not written that.
you see
uh,
this I write E lambda D lambda. Then I multiplied it with E lambda. Then now I can write EB lambda. Okay. Okay, I think you got confused. I written this. Both are same only. Now we will understand. So I replaced in both numerator and denominator, or I substituted, I converted it with respect to black bodies by multiplying it with emissivity.
yeah, now it is okay, sir.
Yeah. So now we have to split this up from 0 to 4, 1 d lambda plus equals 4 to 6 EB lambda d lambda divided by L 0 to infinity E lambda EB lambda d lambda. Okay. So now I am clipping this. So write it here. Okay. Now I'm replacing it EB lambda from 0 to lambda. It's constant. Then we will have this function that is f 0 to lambda 1 plus lambda 2 f 0 to lambda 2 minus f 0 to lambda 1 whole divided by what is this? This we integral 0 to lambda. We already find it out as what? We already found this expression.
Yes, sir.
This is emissivity value epsilon. Okay, by epsilon. Now you just need to find out what is these fractions. Can you find it out? So lambda 1 t is 400 micrometric, sorry, 4000. Okay. So this we already find out 0.48. Now you can just substitute the required fraction 0.8 into 48 plus 0.6 into 0.7374 minus 0.4805 all divided by 0.7224. Can you please calculate and say what is this answer? So
0.75.
Yeah, close to 0.7. So this is the fraction of radiation which is actually between this 0 to 6 uh, micrometer wavelength. So now in this question, it's a continuation of the previous question. What should be the emissivity of a gray body at 2 1200 Kelvin?
Actually, please, will you please show the statement of question number 8? Uh, Sir, here can't we directly take the temperature we are having 1000 Kelvin and we can multiply it by 6 micrometer it is there, then directly we will be getting it 0.74.
Which one I think? Which one? Which one?
Okay, so this calculate the fraction of total emissive power in the
Yeah,
in the region you are writing 6 to 6 micrometer.
yeah.
Can't we directly do it that 6 micrometer multiplied by 1000, 6000, we are getting that black body, and then we can directly get it from 0.7.
So that is what I told. That is for black body radiation. This is not black body. This is a gray body. You have to consider the emissivity also. Yeah, if it was a black body, then you can whatever you say is correct because that function is black body radiation function. But this in this question, it's not a black body. It has a certain emissivity in the particular range. Okay, it's the diffuse surface. I hope it is clear.
But sir, when it is a diffuse surface, isn't it a black body?
No, 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 no. How can we say diffuse surface as a black body? The diffuse surface has a particular what to say. Uh, it is independent. The intensity is independent of direction. That's all. It will have spectral distribution of wavelength, and also it will have different emissivity at a different emissive power at a different wavelength. Diffuse and black bodies are not same.
Okay, okay, sir.
If there is emissivity given, it's not a black body. Okay. A diffuse surface means it is, we generally say it as a gray body. But if the emissivity values are given, it's not a black body. Okay. So in this question, we have to find out what is the total hemispherical power as this calculated in the question. So for the emissivity of a gray body to have the same uh, gray body at 1200 Kelvin to have the same hemispherical total emissive power as this body. That is what we have to find out. So that is EB. The emissivity of the body is sigma 4. Okay. So just we are asked to find out what is this epsilon if it is 1200. Okay. Kelvin. That is, we already find it out what is the EB. So divided by,
Actually, sir, when you are multiplying it by emissivity, then it should not be EB, it should be E.
yeah, okay, it should be. So this you can calculate later. This will come out to be around point some close to 0.34. Okay. So now this is a great question. Okay. I hope you will be able to solve it. So in this region we are given uh, T1, T2, T3. Okay, and T1 is greater than T2 greater than T3. These are the given values. Okay, given data. And we are given a spectral body emissive power versus wavelength at three different temperatures, and its temperature relationship also given. So you have to find out what is the correct statement. Whether this graph is correct or not, that is asked.
I think, sir, this graph is not correct
Why?
because at higher temperatures, the maximum wavelength shifts to the shorter side. And here at the maximum temperatures, the maximum wavelength is shifting to the higher wavelengths.
Yeah, right. So here, if I write, this is the line connecting the maximum point. So this is, if I am writing this as lambda 1, lambda 2, lambda 3. Okay. So we, from the means displacement law, we know lambda max t should be a constant. Okay. So when the temperature T1 is greater than T2 is greater than T3, so in order to satisfy this, what should be there? Lambda max of 1 should be less than lambda max of 2, which it should be less than lambda max of 3. But here in this case, it's opposite. That is lambda max 1 is greater than lambda max 2, which is greater than lambda max 3. Okay. So hence, if T increases the according to Wien's displacement law, the lambda max, the wavelength at which the maximum emission happens, should be maximum emissive power happens should be decreased. Okay, but according to this figure, it's the reverse. So hence, the Wien's displacement law is not satisfied. So this figure is wrong. So
So, sir, what should be the option? Option should be D.
D, yeah. So this is a gate question. So I can I don't remember the actual year, but this was a gate question. That's I'm sure. So yeah, today this comes to the end of our session. So I hope this session was helpful for you, and you will be able to solve. And I think you are comfortable with the tables, black body radiation tables now. I think uh, you're seeing it for the first time, or
First time, sir.
yeah. So this kind of questions can be asked, but uh, it's not sure that it will be asked in this in this final examination of this course. But in the from the radiation point of view, this black body radiation function table, it's little bit important, but because it can be asked in the semester exam or other type of examinations. Okay, so it's just in
Okay, sir. Thank you.
yeah. Thank you for joining, and have a nice week ahead. And
Same,
see you in the next week. Thank you.
same to you, sir. Thank you.